So students, let's start the new chapter, that is the S block elements. That is chapter number 10. Okay. So let's start this chapter, this S block element. So the first element of the alkali and alkaline earth metal differs in many respects from other members of the group. This is the first statement which has been stated in the NCERT book of yours for the chapter, that is the S block element, that the first element which is present in the group of alkali or alkaline earth metal, which are the first group and the second group of our periodic table, they are differing in many respect to the other members of the groups which are present there. Okay, so with this particular code, let's start this chapter. So here we are going to study about the S block elements. So first let's define what is this S block elements. Okay, so the elements in which the valence electron are filled in the S suborbital S orbital is called are called S block elements. Okay, so the elements where we will see that the last element are filling up in the S block, okay, or the S orbital, they will be termed as what? They will be termed as the S block elements. So the general electronic configuration of these elements will be ns12. Okay, ns0 to 2, sorry, ns12 it will be. Either the S orbital will be having one electron or either it will be having two electrons. Okay, and this will be the valence shell. This will be the valence shell for the S block orbitals or S block elements. Okay, so in the periodic table we will see that if we are talking about the periodic table, then in the periodic table we will see that the first group and the second group, they both are having this property, that the elements which are present in both this group, they are having what? They are having the electrons filled up in the S block element, S shell. Okay, so if you are talking about the elements of the group 1 and group 2, okay, if you are talking about the elements of group 1 and group 2, so group 1 elements, the group 1 elements are called as alkali metals. Alkali metals, and the alkali metals are lithium, then sodium, then sodium, then potassium, then after that lithium, sodium, potassium, then after that rubidium, not Rb, I think so it is Ru. Okay, rubidium, no, it is lithium, Rb it will be rubidium, and then cesium, and last is the, after cesium, last is the francesium. That is Fr. These are the elements which are present here in the group 1. The atomic number will be 3 plus 8 11 plus 8 19 plus 18, that is 37, plus 18, that is 55, and plus 32, that is 87. Okay, so this will be the electronic atomic number for the group 1 elements, that is alkali metals. And if you are talking about the electronic configuration or the valence shell configuration here, then it will be 2s1, 3s1, 4s1, 5s1, 6s1 and 7s1. Means all these are the elements which are having one electrons in their outermost subshell, and the shell you can see out here how it is changing from second to seventh. So it means the elements here are varying from first period to the seventh period, sorry, second period to the seventh period here. Next is the group 2 elements, which are called as alkaline earth metals. Alkaline earth metals. In this group, the elements are beryllium. I think so. One R here it will be beryllium. Then the next is magnesium. Then the next is calcium. Then the next is strontium. Strontium. Then the next is barium. And the last is radium. Okay. The electronic configuration here it will be for barium it is 4 plus 8 it will be 12 plus 8 it will be 20 plus 18 it will be 38 plus 18 it will be 56 and plus 32 it will be 88. The final electronic configuration of the valence electronic configuration here it will be 2s2, 3s2, 3p0, 4s2, 4p0, 5s2, 5p0, 6s2, 6p0 and last will be 7s2, 7p0 here. Okay, so this is the first group and second group, that is the S block elements which are present in our periodic table. Okay, now let's talk about here why the elements or the first group elements are called as alkali metals or alkaline earth metals. So the reason here is that these are so called because they form hydroxides on reaction with water which are strongly alkaline in nature. Okay, so to understand this thing, let's see some of the chemical reactions. If sodium is reacted with water, so here 2Na will react with 2H2O to form 2NaOH plus H2 gas. Okay, so here we will see that plus a large amount of heat will also be released out here. So here NaOH has been formed. Similarly, when Mg is reacting with water, then here magnesium hydroxide is been formed, but not a very large amount of heat will be released out here. Okay, so this kind of reactions where we are seeing that hydroxides are formed, metal hydroxides are formed, which are having a highly basic nature. Okay, which are having highly alkaline nature. So therefore we will see that the elements which are present in the group 1 and group 2, they are termed as what? They are termed as alkali metals for the first group, and for the second group, they are so called because their oxides and hydroxides are alkaline in nature, and these metal oxides are found in earth crust. Okay, for example magnesium, okay, calcium, these are one of the abundant elements which are present in our earth crust, and the oxides which are found out in the earth crust, they are having a very high basic nature. Okay, they are having a very high basic nature, and due to this reason they are termed as what? They are termed as the alkali earth metal or alkaline earth metals. Next, Among the alkali metals, sodium and potassium are the abundant, and lithium, rubidium, and cesium have very small amount. Okay, very small amount, as we are going to compare that the sodium's abundance and the potassium's abundance, the lithium, rubidium, and cesium, they both, these three are having very less amount in the earth crust, while the francesium, it is present in very small amount. Okay, because it is a very highly radioactive substance, and it cannot be present for very long time in the form of francesium. Okay, and its half-life is only for 21 minutes. Okay, here you can see that the half-life for the francesium isotope, that is 223, francesium's 223 isotope, it is only of 21 minutes only. So it means that if we are able to produce a francesium atom, then it will only last till 21 minutes only before being changed up into the next element. Okay, of the alkaline earth metals, calcium and magnesium are the fifth and the sixth abundant elements on the earth crust, while the strontium and barium have much lower abundance, and the beryllium is one of the rare, and radium is the radioactive. Okay, it is one of the radioactive which are present in the igneous rocks. Okay, which are present in the igneous rock. So earth crust can be understand as the layer, the thinnest layer of the land which is present on the earth. It is termed as the earth crust. Okay, and the igneous rock, these are the rocks which are formed from the magma. Okay, that is the molten rock which are been erupted out from the earth's mantle. Okay, so there are rocks which are formed after cooling down of this mantle. That particular rocks are termed as what? They are termed as the igneous rocks. As I have told you that the general electronic configuration for the S block element is NS1 or NS2 only. Okay, so let's move further and see the next topic for this chapter, that is the lithium and the beryllium families talk. Okay, so lithium family is termed as the lithium family is termed as the group 1, and the beryllium family is termed as the group 2. Okay, and here we will see that the lithium and beryllium, being the first element of their groups, they are having some properties which are very much different, or which are possessing anomalous properties as comparison to that of their group members. Okay, so hence we can conclude that the lithiums show similarities to that of the magnesium. Here we will conclude that the lithium, okay, they are having a diagonal relationship with that of the magnesium there. If I am going to see the positions of magnesium and lithium in the periodic table. So here we can see that lithium, it is placed here below that sodium, potassium, rubidium, cesium, francesium. Similarly, beryllium, magnesium, calcium, strontium, barium, and radium. So here we will observe that the lithium is having some of the relativistic similarities between the magnesium and lithium here. Okay, and this kind of relation. Similarly, the beryllium will be having some of the relative properties which are related to the aluminium, which was present in the 13th group, that is the boron family. Okay, so this type of relations which is aligned out here between the lithium and magnesium and between the beryllium and aluminium, this particular property is termed as the diagonal relationship. Okay, it is termed as the diagonal relationship of the first element of the alkaline earth metal and alkali earth metals. Okay, alkaline earth metal and alkali metals. So what is this particular relationship? Let's talk about this. The diagonal relationship is due to the similarity of their ionic sizes. What is the reason why they are having this diagonal relationship? The reason is that they are having the similar ionic size or similar radius ratio of the elements. Okay, they are having the similar radius ratio for the elements, such as monovalent sodium and potassium ions and divalent magnesium and calcium ions are found in large proportion in the biological fluids. We will see that the Na plus, K plus, okay, and Mg2 plus and Ca2 plus, these are one of the important constituents of the biological fluids. These ions perform important biological functions such as maintenance of the ion balance and nerve impulse conduction also. So they are one of the important biological elements also. Okay, if you are talking about the sodium or potassium or magnesium or calcium here. Okay, let's move further and see the next topic, that is let's start talking about the alkali metals, that is the group 1 elements. Okay, so alkali metals, they are having a regular trend in their physical and chemical properties with the increase in their atomic number. Okay, we can observe that there are regular trends in their physical and chemical property when we are obtaining the relationship on according to their increasing atomic number. The atomic, physical and chemical properties of alkali metals can be started with the discussion of their electronic configuration. Okay, so as we are starting the discussion with the electronic configuration, so here we know that the general electronic configuration which we have considered for the alkali metals, it has been taken as N-S-1. Okay, so here you can observe that for lithium, the electronic configuration will become 1s2 2s1. For sodium, it is 1s2 2s2 2p6 3s1. For potassium, it is 1s2 2s2 2p6, or we can say that this is the argon. Okay, argon, and then 4s1. Similarly, that we can start here for rubidium, it will be xenon. Then after that xenon, it will be 5s1. Then for here it will be krypton. Then krypton it will be 4s2, and last here it will be sorry, for rubidium it is krypton and 5s1, and for cesium it is xenon and 6s1, and for last radon 7s1. Okay, for francesium it is radon then 7s1. So this is the general electronic configuration or electronic configuration for the um, group 1 element, or that is the alkali metals. Also, as they are having only one electron in their outermost shell, or they are having only one electron as their valence electron, so here naturally, as being metals, they will be losing the electrons, and hence they will be possessing a they will be having a tendency to form a monovalent ion. Okay, they will be having a higher tendency to form a monovalent ion. So let's move further and see the next topic, that is the ionization enthalpy. Okay, ionization enthalpy. Acha, one more thing which can be discussed out here. As we are moving down in the group, we can see that from lithium, from 1s2 to 2s1, on moving till the francesium, here we will see that 7s1. Okay, so the last electronic, the last element, the last electron which is filled out here in the francesium is 7s1. So here the size is increasing, and with the increase in size on going down in the group, we will see that the chances of donation of electrons, it will also increase out there. Means the lithium will be having lower tendency to donate the electrons, while we will see that the francesium, it is having the highest tendency to donate the electrons. Why? The reason is that on moving down in the group, we will see that the size of the atom is increasing, and the outermost electron is more farther as comparison to that of the first element in the last element. Okay. Also, we can observe this thing, that they increase in size while going down from lithium to cesium will be seen out there. Okay, the atomic and ionic radii of alkali metal increases on moving down in the group, that is the increase in size while going from lithium to cesium can be observed out there. Okay, next is the ionization enthalpy. So everybody knows that ionization enthalpy means what? The tendency of an electron to, the tendency of an atom to lose electron. Okay, so the ionization enthalpy of alkali metals are considerably very low. It is very low. Okay, and due to this reason, when we are moving down in the group, it decreases more. From moving cesium to lithium to cesium, we will see that this energy also increases more, sorry, also decreases more with the increase in size, and hence the tendency to release electron increases out there. Means cesium will be more reactive as comparison to that of the elements which are present in the higher position, or the earlier position in the group. Okay. Next is the hydration enthalpy. So the hydration enthalpies of alkali metal ions decreases with the increase in ionic size. We will see that the hydration enthalpy has been increasing out there. It means that lithium will be having the highest hydration enthalpy as comparison to that of the sodium, then as comparison to that of the potassium, then as comparison to that of the rubidium, and then as comparison to that of the cesium ion. Lithium ion has the highest maximum degree of hydration, and for this reason lithium salts are mostly hydrated salts. We will see that the Lithium salts are forming the mostly hydrated salts, so as comparison to that of the other salts which are present in this particular group. Next is the physical properties of the alkali metals. So alkali metals are generally silvery white in color. They are soft, okay, and they are light metals. They are very light metals, okay. For example, sodium, potassium, they are really soft, that can be easily cut out with spatula easily, okay. Also cesium and that one is your rubidium, they are all having so much lower melting point that they can be easily melt out in the under our palm only, okay. By keeping them for few minutes in our palm, we will see that the cesium can be easily melted out there, okay. The particular melting point of cesium is that much low, okay. Next, sodium and potassium are the lightest, okay. So here one thing is there, that potassium is lighter than that of the sodium here. And this is due to the presence of lower density here, okay. In the case of potassium, we will see that it is having lower density as comparison to that of the sodium, and hence potassium is lighter than that of the sodium here. Next, the melting and boiling point of the alkali metals is also very low, indicating their weak metallic bonds due to the presence of only a single valence electron in them. The alkali metals and their salt imparts characteristic colors to an oxidizing flame. If we are making some salts of the alkali metals and we are burning it, then we will see that they will be producing a characteristic color flame there. So which kind of flames can be produced out there? So this is because due to the heat from the flame excites the outermost orbital electrons to a higher energy level, and then the electrons come back to their ground state by radiating all the energy which has been absorbed by them. So in doing so, on moving back to the ground state there, they will release the energy and they will radiate the energy which is in the visible range only, and hence we will see that the different characteristic colored frames are produced when we are heating this element. So if lithium is heated, then it will be burning with a crimson red flame, okay. It will be burning with a crimson red flame, while the sodium will be burning with a yellow flame, while the potassium will be burning with a violet flame. The red violet flame will be there for the rubidium, and the cesium will be burning with a blue flame here, okay. So these are the characteristics oxidation flames which are produced by the different salts of the alkali metals. Next, alkali metals can be detected with the respective of their flame test also. We can easily detect by the flame test that the which of the particular element is being present out there, and it is and can be determined by the flame photometry or atomic absorption spectrometry also. These elements, when irradiated with light, the light energy absorbed may be sufficient to make an electron to make an atom to lose the electron. So much lower ionization enthalpy is required that it is easy, very easy to remove an electron from the outermost shell of that of an atomic metal, that is alkali metal, atom of an alkali metal. Let's discuss about some of the terminologies related with the. Okay, let's have some introduction to the elements, different properties which are related out here. So first here is the atomic number. So atomic number I have discussed with you previously only, that they are having atomic number as 3 for lithium, 11 for sodium, 19 for potassium, 37 for rubidium, cesium 55, and francesium 87. Atomic masses, lithium is having 7, 6.94, it can be considered as 7, 22.99, that is 23, 31, 39, sorry, for potassium it is 39, for rubidium it is 85, for cesium it is 133, for francesium it is 223. Electronic configuration: 2s1, 3s1, 4s1, 5s1, 6s1, and 7s1. We have discussed this before also. The ionization enthalpy for the lithium, we will see that it is 520. Then for sodium, it is lower, which is 496. Then for potassium it is more lower, which is 419. For rubidium, 403. Then for cesium, which is 306. And for francesium, it is near about 375. It means that when we are moving down in the group, we will see that there is a decrease in the ionization enthalpy. Next, the hydration enthalpy. So the hydration enthalpy is negative 506 for lithium, which is having the highest hydration enthalpy, and due to this reason they are having the highest hydrated salts. Okay, lithiums are having the highest hydrated salts in the whole group. Next is the 406 for sodium, minus 406, minus 330, which is greater than that of the potassium, that is sodium. Then rubidium 310, which is greater than that of the potassium, and minus 206, which is greater than for that of the rubidium here. Francesium salts, hydrated salts are not known till now. Next is the metallic radius. So metallic radius for lithium is 152 pm. For sodium it is 186 pm. For potassium it is 227 pm. For rubidium it is 248 pm. For cesium it is 265 pm. Okay. So on moving down in the group, we can see that the metallic radius is increasing out gradually. Next, here in case of potassium, you can observe that there is a sudden change here. A very rather drastic change of the metallic radius has been seen out here, and this is due to the presence of the D block in the potassium. In the sodium case, we cannot see the presence of the D block, but here in the potassium case, the presence of D block, which causes the a sudden increase in the density, sudden increase in the size of the potassium atom, and hence the density of the potassium atom, the potassium metal is been decreased out there, and due to this reason, what will happen? We will see that there is a drastic size change here, okay, in between the sodium and potassium. Next is the ionic radius, 76, then 102. Here also a very large change is seen out here. Then 138, 152, 167. Okay. And this is the reason here is that as lithium is having very smaller size, okay, and the nuclear charge is very higher there. So due to this reason, we will see that the ionic radius of lithium is very small, and due to this reason, the releasing of electron density, the releasing of electrons from their outermost shell, it will be lower chances in the lithium, while in case of that of the sodium and potassium. Next is the melting point. In the melting point, we can see that lithium is having 554. For sodium, it is 371. For potassium, it is 336. For rubidium, it is 312. For cesium, it is 302. Okay. Next, boiling point 1615 for lithium, which is highest one. Then for potassium, sodium and potassium, you can see that it is much lower than that of the lithium. Okay. And for cesium and rubidium, it is very, very lower, 944 and 961 only. Next is the density. Here lithium is having 0.53, 0.97, 0.86, 1.53 and 1.90. Okay. The standard electrode potential, lithium is having minus 3.04, minus 2.714, minus 2.925, minus 2.930, and minus 2.927. Occurrence in the lithosphere, it is having the 18%, it is having 2.27%, it is having 1.84%, 78 to 12 percent parts per million only, and 2 to 6 parts per million only, and it is having less than 10 to the power minus 18. Okay, very, very lower presence there will be for the francesium here. Okay, so these were the discussion about the first group elements here for their physical properties. In the next class, we are going to discuss about the chemical properties and the different kind of trends which are being followed out here for the alkali metals in our periodic table. So for today's class, I'm ending the class here only. We will meet up in the next class. Thank you.